Bismillahirrahmanirrahim. Now, EWMA, yeah, exponentially weighted moving average control chart. Now, for EW control chart, or we call it Ewma, for Ewma control chart, what we're going to plot on the control chart is actually EWMA statistic. Yeah. Before this, if you have a look at QSER, we plot C, the value of C, and for the normal control chart, Sheward control chart, we plot the value of X itself, the individual measurement values or the X bar for the respective sample mean. Yeah. Now, the Ewma statistic can be obtained by using this formula. Yeah, Ewma statistic is denoted by this symbol Z. Yeah, Zi for the individual observation equals to lambda x1 plus 1 minus lambda Z1 minus 1, I minus 1. So this Z I minus 1 is the succeeding Z value in comparison to the Z of I itself. So lambda normally range from the value of 0, is larger than 0, smaller and equals to 1, meaning to say lambda will be larger than 0, but smaller or equals to 1. So lambda is a constant, and the starting value of Z naught will be equals to mu naught. Okay, so this mu naught, this mu naught is actually the process mean value. Okay, or if you talk about phase 1, mu naught will be obtained from phase 1. Okay, we have discussed how EWMA and QSER can be used for second phase. And we also have looked at how Sheward control chart is more suitable for phase 1. So as you know, at phase 1, we will estimate the parameter which are mean and standard deviation. So similarly here, those two values will be employed, will be used, will be applied in the second phase. So for example, in the second phase, we use Ewma control chart. Therefore, the starting value of Ewma statistic will be mu equals to 0. Okay. So Ewma Z statistic is a weighted average of all previous sample means and can be expressed in terms of this formula, whereby Z equals to lambda times 1 minus lambda to the power of J times X from X for I minus J, from J equals to 0 to I minus 1, okay, plus 1 minus lambda to the power of I times the initial Z statistic, or we call it Ewma statistic. Okay, so that is the general formula for Ewma Z statistic. So again, this is the formula where the initial Z will be equals to mu naught. Now, the Ewma Z I is actually a weighted average of all previous sample means and can be expressed in terms of this formula, as we have mentioned just now. So if you look at the last bit, which is Z statistic of the preceding observations, Z I minus 1. So this is actually equals to the formula of lambda times X I minus 1 plus in bracket 1 minus lambda Z I minus 2. So if you look at the formula carefully, for Zi, it will be lambda xi plus 1 minus lambda times Zi I minus 1. Yeah. Therefore, the value of z for I minus 1, yeah, can be computed by this formula, which is lambda times x I minus 1. Yeah, I minus 1. This is xi. This is x minus 1, which is similar to the z statistic itself, plus 1 minus lambda times zi minus 2. Yeah, so this is the formula which will continue, yeah, for each and every z statistic for the respective observations. Okay, so continuing to substitute recursively for z I minus j, where j equals to 2, 3, 4 until t, yeah, the total number of observation, we will obtain this formula. Okay, we will obtain this formula. Okay, so this part is actually the summation of 1 minus lambda to the power of j times x I minus j. Yeah, so this bit, yeah, this bit is actually the weighted part of the formula. Yeah, plus 1 minus lambda to the power of I times z naught, yeah, which is the initial z value. Now, so therefore, the weight of lambda times 1 minus lambda to the power of j will decrease geometrically with the age of the sample mean. Yeah? Meaning to say that the weight, yeah, the weight part of the formula will be reducing, yeah, at the geometric level, yeah, or the geometrically, as the sample mean increase in time. Now, so this is what I mean by with the age of the sample mean. As the sample mean increase in time, you know, from time 1, 2, 3, 4, 5, so on and so forth. Yeah. So the time is increasing. So when time is increasing, the weight of lambda times 1 minus lambda to the power of j will decrease geometrically. Furthermore, the weight will sum to unity. Yeah? This whole value, yeah, as time goes by or as your time increases, this whole value will be equals to 1. Yeah. So if we were to rewrite, yeah, this part of 1 minus lambda to the power of j from j equals to 0 to I equals to 1, you will have this formula. Yeah, this part, yeah, which is 1 minus lambda to the power of I over 1 minus, in bracket, 1 minus lambda. Okay, so this is the simplification of the summation of the previous part of the weight. Yeah, so from here you will obtain it will equals to 1 minus lambda to the power of I. Yeah, so you will not be asked to prove mathematically. Yeah, so but this has been proven, and we just use it here. Yeah, how we can transform from this part of the weight in terms of summation into this formula. Yeah, this fraction rather. Okay, so whole thing will be equals to 1 minus, in bracket, 1 minus lambda to the power of I. Okay, so what we can do is we can try to plug in values of lambda and try to compute this part, yeah, of the weight, yeah, for each and every individual observations, yeah, or for each and every sample if you are dealing with sample mean values. Okay, so what you're going to do is you're going to plug in values for 1 minus lambda to the power of I. Yeah, so this is the respective value of lambda, which is 0.2 in this case, and I is the number of observations. Yeah, and what we have done here is we find the value of 1 minus lambda to the power of I for each and every observations. Yeah. So as you can see, as the number of observation increase in time, yeah, remember we are dealing with time weighted control chart. So all this must be in terms of time. Yeah, time 0, time 1, time 2, time 3, so on and so forth. So means to say that as time goes up, you will notice that this part, yeah, of the weight will be reducing, yeah, to a, to a stage where it will be close to 0. Like this example, at observation number 25, yeah, or rather 24 here, yeah, the value of weight of which is 1 minus lambda to the power of I will be equals to 0.0038. Yeah, so if you were to plug in this value here, yeah, so it'll be 1 minus a value which is close to 0. Yeah, so again, if your times increases as time goes by, this part of the formula will be equals to 0. Yeah, it will literally equals to 0. Therefore, 1 minus 0 will be equals to 1. Okay, so this is what it means that the weight will sum to unity. Yeah, as time goes by, this weight, yeah, this value will be equals to 1. Okay, so in graphical form, yeah, if you look at the value of weight here, yeah, so the weight value will be decreasing as time goes by, or as it says here, as the age of sample increases. As the sample mean age, the value of weight will be decreasing. Yeah. So the weight decrease geometrically and connected by a smooth curve as shown by this diagram. Yeah. So this diagram is simply to show you that as time goes by, the weight value will be reducing until it will be close to 0. Yeah. Now, if the observation x are independent and random variable with variance sigma to the power of 2, yeah, the normal individual observations with variance sigma to the power of 2, then the variance of Ewma z statistic will be equals to this formula, which is sigma to the power of 2 itself, or rather the individual observation variance times lambda over 2 minus lambda whole thing times 1 minus in bracket 1 minus lambda to the power of 2 times I. Okay, so basically this is the variance. Yeah, this is the formula for variance for the Ewma z statistic. Yeah, and from this variance we can compute the control limit for the Ewma control chart. And the Ewma control chart, from the Ewma control chart itself, the center line will be mu naught, yeah, which is actually the population mean value. And the upper and lower control limit can be computed by taking mu plus minus L times standard deviation sigma times the square root of variance. Yeah, square root of variance of the Ewma z statistic. Yeah, so take note here. Yeah, so this part. Yeah, this part, the whole thing. Yeah, this is variance. So you're going to take square root of variance for Ewma z statistic. So Ewma z statistic is actually the a standard deviation to the power of 2. Yeah. So when you take the square root of the whole variance, you will get sigma times square root of lambda divided by 2 minus lambda whole thing times 1 minus in bracket 1 minus lambda to the power of 2 times I. Okay, so take note here. Yeah, so this is simply L times the standard deviation, which is actually the square root of the variance of Z statistic, which is the Ewma statistic. Okay, so this is the computation of lower and upper control limit for Ewma control chart, where the center line is actually mu naught itself. Okay, so again, this is the formula of control limit for Ewma control chart. So now, if you look at this formula, we have L, yeah, L. So L, the factor L is actually the width of control limits, yeah. Width of control limit, if you're familiar with K, isn't it? Yeah. So in the in our Sheward control chart, K will be equals to 3. Yeah. So similarly here, it is actually that K that we have looked at previously in Sheward control chart. But in Ewma control chart, it is denoted by L. Okay, it is denoted by L. But they are basically the same thing. Okay. Again, take note of 1 minus in bracket 1 minus lambda to the power of I will approaches unity as I gets larger. Yeah, so this part 1 minus in bracket 1 minus lambda to the power of I itself will be equals to 1 as your times goes by. Yeah, so if your number of individual observation increases, this whole value will be close to 0. As such, you're only left with 1 minus 0, which is equals to 1. Yeah. One thing which is very important for you to note at this stage, especially for Ewma control chart, is that the upper and lower control limit is actually dependent on the value of individual observation I. Okay, so individual observation I actually determine the upper and lower control limit. This means to say that for each and every individual observation, they will have a separate upper and lower control limit. Yeah? For each individual observations, it's going to have its own upper and lower control limit. Yeah? Remember last time we did our control chart with variable sample size. Yeah? On which the control limit is a jagged line. Yeah, it's not a straight line, it's a jagged line. Yeah, we still remember. So similarly, that is the case for Ewma control chart. Yeah, but it's gonna be the same center line, which is mu equals to 0 for all individual observation for each and every observations. Okay. So now the fact that now coming back again to this this point where we say that as I gets larger, 1 minus in bracket 1 minus lambda to the power of I will approach unity. Yeah, so it means that this part of the formula will be equals to 1. Yeah, as time increases or as time goes by, this part will be equals to 1. Yeah. Similarly here, this part of the formula will be equals to 1. Yeah. And therefore, after several period of time, the control limit will approach a steady state. Yeah. So what does it mean, steady state? It means that towards the end of the data set, your upper and lower control limit will become a straight line, okay, in general. So the point where it actually becomes a straight line, that is what we call a steady state control limits. Yeah. So here we have the formula for the upper and lower control limit for the stage whereby it is a steady state control limit. Okay, so we no longer have the formula that we have the part that we have here. Previously, we have this formula, isn't it? Yeah. So when it comes to a steady state, this value will be equals to 1, and therefore the upper and lower control limit for Ewma control chart at a steady state will be equals to mu naught plus minus L times the standard deviation of the Ewma Z statistic. But this time round, this value will be equals to 1. Yeah, this part of the formula that we have looked at earlier on. Okay. So what we're going to do next is we're going to set up a Ewma control chart. We're going to produce, we're going to plot Ewma control chart from the data in table 9.1. Yeah, but for each and every time you would like to plot Ewma control chart, there are two parameters that you have to determine earlier on. This is lambda and also L value. Yeah, we're going to look at in more detail what should be the value, what would be the appropriate value for lambda as well as L for Ewma control chart. Okay, but this time round at this stage, let's assume lambda equals to 0.10 and L equals to 2.7. Yeah, for the data set in table 9.1. Okay. Recall that the target value or the population mean value mu naught is equals to 10 and the standard deviation sigma equals to 1. Yeah. Again, I have to emphasize here that these two values normally has been estimated from phase 1 control chart, and in most cases phase 1 we use either individual measurement control chart or Sheward control chart, depending on the type of data set that we have. Now, to illustrate the calculation of Ewma control chart, Ewma Z statistic, we have to consider the first observation. Yeah, so if you still remember in table 9.1, the first observation x1 is equals to 9.41. Okay, so the first value of Ewma is equals to z. Is z equals to, we're going to use this formula, which is lambda times s1 itself plus 1 minus lambda times z naught. Yeah, so z naught is the initial Ewma Z statistic. Yeah, so we have also known earlier on that for the first or the initial Ewma statistic, it will be equals to the population mean value. Yeah, in this case, it is equals to 10. Yeah, therefore, by plug in the value of lambda equals to 0.10, x1 equals to 9.45. Yeah. Plus 1 minus lambda. So 1 minus lambda is 1 minus 0.1. We got 0.9 times 10. And that will give us the first Ewma Z statistic Z1 equals to 9.945. Okay. So now we have got the value of the Ewma statistic. Z1 equals to 9.945, yeah, as the first value plotted on the Ewma control chart. Yeah, and we can now compute the second value of Ewma by using exactly the same formula. This is Z2. Yeah, the second value of Ewma statistic equals to lambda x2 plus 1 minus lambda z1. Yeah, remember, if we are computing for z2, the value of z here will belong to z1. If you are computing z1, this z will be equals to z0, or the initial z value. Okay, now by plugging in or substituting the value of lambda equals to 0.1, x2 equals to 7.99. Yeah, this is the second value in table 9.1 plus 0.9, which is 1 minus lambda. 1 minus 0.1, we got 0.9 times z1. So z1 is equals to 9.945. And that will give us z2 equals to 9.7495. Okay, so those are the computation that we have looked at, how we can compute Z1 and Z2. The other values of Ewma statistic are computed similarly. Yeah. So from here we can see all the values of Ewma Z statistic for each and every value given in table 9.1. Yeah. So all these are actually the individual X values. Yeah. And here is the Ewma Z statistic. Okay. Now let's look at now how we can compute the control limits. Yeah, remember as I told you earlier on, the respective upper and lower control limit for each and every observation are not the same. Yeah, especially for the first few observations. Now, given the formula of upper and lower control limit, okay, we have looked at this formula earlier on. We can plug in or we can substitute the respective value of mu naught L, which is equals to 2.7, as we have informed earlier on. Standard deviation of sigma equals to 1. Yeah, and we do the computation for the other part, for the rest part of the standard deviation. Yeah, and we do both for upper and lower control limit, and we got the value of 10.27 for upper control limit and 9.73 for the lower control limit. Yeah, remember these two values are the upper and lower control limit for the first observation, or rather for the observation at period I equals to 1. Yeah. Now we can also do the same for the second period, period 2, where we compute the limit by substituting the respective value of, again, process mean equals to 10, L equals to 2.7, lambda equals to 0.1, and we will get upper control limit equals to 10.36, lower control limit 9.64. Okay, so these two are the upper and lower control limit for the observation or for the sample value at period 2. Okay. Now, from figure 9.7, we're gonna 9.7 is actually the plot of Ewma control chart. Yeah, I'm gonna look at this later on. From this figure, we can see that the control limit increases in width as I increases from 1 to 30, yeah, to the value until they stabilize at the steady state values given by this following equation. Yeah, so later on, if you look at the Ewma control chart, yeah, for the first few values, yeah, the upper and control limit will be increasing. Yeah, the gap from upper and lower control limit is widening. Yeah, as time goes by. Yeah, as time period increases, yeah, the width will be also increases. Yeah, the width, the gap between upper and lower control limit, until a stage where you will see this line level off. Yeah, it starts to level off and start to become a straight line. Yeah, so this straight line is actually the steady state of limits. Yeah, steady state of limits, like we have discussed earlier on. Okay, so for the steady state limits, the formula of upper and lower control limit is given by mu plus minus L times standard deviation square root of lambda over 2 minus lambda. Okay, so these are the respective formula, and we can find the value of upper and control limits at the steady state. Yeah, which is equal to 10.62 for upper control limit and 9.38 for lower control limit. Okay, but we can also see that the Ewma control chart signals that observation 20, it is actually the situation of out of control. Yeah, as you can see here. Yeah, 20, it start to increase. Yeah, until the last one. last 2 points rather, yeah, I would say these 2 points it actually exceed the upper control limit, and we say at this situation the process is not in statistical control. Okay, so this is our very own JMP Ewma control chart. Yeah, the early one is from Minitech. Yeah, it's from Montgomery. This one from JMP. Yeah. Now, in general, it was found that the values of lambda is in the interval of 0.05 to 0.25. Yeah. So, in general, lambda within this range works well in practice. Yeah. So, the normal value of lambda will range from 0.05 to 0.25. Yeah. Um, the more popular choices would be lambda equals to 0.05, lambda equals to 1.0, and lambda equals to 0.2. Yeah, so these three values of lambda, the more common values of lambda, yeah, used for Ewma control chart. Now, a good rule of thumb is to use smaller values to detect smaller shifts. So if we know that our process actually experiencing smaller shifts, yeah, in the values, yeah, in the mean values, so we rather use smaller value of lambda. Yeah, smaller lambda meaning the smallest will be 0.05. Okay. Now L. L equals to 3 is the usual 3 sigma limits. Yeah, as I mentioned just now, in the normal Sheward control chart, this is K. Yeah, K equals to 3. In Ewma control chart, this is denoted by L. Yeah, L equals to 3 is the usual limits. And it works reasonably well with the larger value of lambda. Yeah, means to say that if your lambda is small, which is less than 0.1, then the value of L can be reduced to between 2.6 to 2.8. Yeah, so these are the values. So what we have used just now in the earlier example for table for data in table 9.1 is L equals to 2.7. Remember? Yeah. So that is when we use lambda equals to 0.1. Remember? Yeah. So the smaller your lambda, the smaller should be your L. Yeah. And this small meaning the value should be from 2.6 to 2.8. Yeah. The larger one will be equals to 3. Yeah. The normal is equals to 3, especially if your lambda is large. Okay. Okay. So that's all for Ewma. During class, we're going to look at some other data set where we will plot the QSUM as well as Ewma control chart. Okay, so till then, bye bye.